So hi, I'm Olivia, and I'll be presenting on behalf of me and Sven on our work in specification-driven machine learning. And the motivation for this work is that, as we all know, machine learning models are not robust. So we can seemingly achieve incredible accuracy on benchmarks like ImageNet, and yet if we just make a small perturbation to an image like the panda image with some invisible noise that we can't see with our own eyes, then the model will give extremely confident prediction of a completely different class. And we also have this issue that models are prone to learning shortcuts and exploiting spurious correlations. And this leads to very poor performance under distribution shift. So here we're showing some examples where this can arise. So for example, if we're used to seeing objects in certain locations, then they may do poorly if seen in new locations. We may only have certain examples of certain cultures, which then means that the model doesn't work in other locations or cultures. And we also may have capture bias, where most images, for example, of mugs are often taken right-handed. So then it may not work if it's a left-handed image of a mug. And these issues are not limited to just ImageNet. We also see these in other models, such as for CLIP or for language models as well. And kind of what we see is this meta problem is that we have some data or experience and it's biased or it's limited and it's sensitive. And so when we apply simple standard machine learning training to it, then we're going to end up with a model that, or agent that is similarly not biased and thereby, or similarly biased. So it's not robust, it's not safe, and it's not private. And the kind of the way that we have been thinking about handling this problem through our various works is by using specification-driven machine learning. So the idea is that we have some rules or set of specifications, and can we use those specifications to drive training? And thereby, can we obtain models that are unbiased, robust, safe, private, and potentially calibrated? So that's the framework that we'll be thinking about this in order to achieve robust machine learning. And in order to do this, there's two requirements. So first, we need to formalize the specifications. This is the what. And the second is we need to enforce those specifications. So this is the how. So to formalize specifications, one thing that we would want, if we actually want such a thing to be useful in the real world, is to be able to provide a language that can describe the desired behaviors. And we can think about this at different levels of granularity. So for example, that adversarial examples should not alter the classifier predictions, that synonyms should not change the meaning of a sentence, or uncertainty should increase with sensor noise. And finally, that's, for example, lighting conditions or skin tone should not affect classifier performance. And then we also have thought about how can we develop methods in order to enforce these kinds of specifications such that we can make ML systems compliant with these requirements. And one approach is simply to use data augmentation, and that's simply to make our models robust to the specification that if we simply rotate or translate an image, then our model should be robust to that. Another example would be adversarial training, where we have a very clear specification from the LP norm ball that anything within that ball we should classify correctly. And then we also have model certification and verification. And the group, especially Sven, has been working on this kind of approaches for a long time, and there's done a lot of work in this area. And so we'll be focusing on two examples of this specification-driven ML. So the lighting conditions or skin tone should not affect classifier performance, and on how to achieve state-of-the-art adversarial robustness. So just to be clear, I am presenting this on behalf of Sven. This is not work that I have done, so I will do my best to make it clear. And if you have any questions, please just do ask, and I think Sven is around, so can answer in the chat. So the question for adversarial robustness is, what are we solving? So the aim here is to build models that are robust to imperceptible perturbations. And here the perturbation is that if we have an LP norm smaller than some threshold epsilon, then we want our models to be robust within that epsilon ball. So if we take this image of a panda and we add some noise to it, then a normally trained model is going to misclassify the image, but we want to make our model robust to that. And so with adversarial risk, the function or the constraint that we're trying to train over is that we have some so we have our delta within our epsilon norm wall, and we find the delta that is going to make our model fail, and then we want to train such that our model does not make these kinds of failures. And so you can think of it as like a specification. So under this LP norm ball, that if we modify the image, then we're going to maintain the specification that the model is always correct. And so adversarial training works like in the, so here we use kind of the standard PGD adversarial training. So we have an inner optimization, which is finding a delta or a perturbation that we apply to the image. That means that the model misclassifies the image, and then the outer optimization is making sure that for all of these cases, how do we actually get the model in order to predict the right result? So there's a number of challenges of adversarial training. So while this like kind of formulation was set up a while ago, and people have been working on this for a long time, there are some bottlenecks that have arisen. And one of these bottlenecks is that there is a trade-off between clean and robust accuracy. So that if we try to improve on robust accuracy, then we're going to use the model capacity on doing that. And so then we're going to say do worse than the clean accuracy and vice versa. So then how do we trade off these requirements? And then also we find that using more capacity with the model improves robust training. And so, you know, maybe we want to scale the model more and more, but then we're going to start hitting the limits of the ability to actually scale these models. So yeah, so prior work has demonstrated that robust training benefits from larger networks, and this may be because of the theoretical relationship between the number of neurons and smoothness. And also we find that with more data that adversarial training does better. So previous work has demonstrated that robust training requires significantly more data than standard training. And so if we just have the standard supervised setup, then how are we going to go about collecting 40x or even more data? And so this work that we did in the past couple of years was looking at how can we really, without necessarily using an auxiliary data set, how can we leverage either standard techniques from supervised learning of using data augmentation, but also more interestingly, how can we use generated data in order to satisfy that kind of constraint of always requiring more data with adversarial training? And so the motivation here was that, as we were saying before, that there's this kind of inherent requirement with adversarial training of requiring substantially larger data sets. And so other works used additional unlabeled data to improve robustness. And so what we find here is that with our method, which, so I think this is like the previous state of the art, and with our method, we're going to exceed on the state of the art. And so we demonstrate that it is possible to use low quality generated inputs to improve robust accuracy on cipher 10 against L infinity perturbations of size epsilon equals 8/255. And to do this, we leverage higher quality generated inputs. So the idea is that we're going to use generated models trained on the original data, and then use this to generate additional data and demonstrate that with this, we can achieve improved performance. And that actually using the best model, so DDPM, we can achieve a robust accuracy of 66 on cipher 10, which is an improvement of 8.96 upon state of the art. And that this approach we can also use on other data sets like cipher 100, SVHN, and ImageNet. And just a reminder, we're not using any additional external data. This is all just done with the original data set. And so the strategy is as follows. We have some training data set. I'm not sure if you can see my pointer, but I hope so. You have some training data set. You use this to first train a non-robust classifier, which can give us pseudo labels. We also use this training data set to train an unconditional generative model, which generates a bunch of images, which we can label with our pseudo labeler. This gives us a generated data set, and we combine the generated and training data set in order to train our robust classifier. And using this, we'll get a lot more synthetic examples, which are potentially going to make our robust classifier more adversarially robust. Okay, so now let's look at some preliminary results. So initially, we just took a very simple generative model, so a conditional Gaussian fitted over the CIFAR 10 training set. And you can see the images look like this, so they're pretty bad. But we add these samples in different proportions while training. So for example, this would be 80% real and 20% synthetic. And now here we look at the performance as we vary the amount of real data. So we're showing robust test accuracy as a function of the proportion of real data. And what we can see is that with some combination, so this 80-20%, then we're able to actually improve over using just real data and improve by about 1%. So even with this really bad synthetic data, we're able to improve robustness. So then the question is, why is this working? And we hypothesize that there's robustness can be improved if first we have accurate pseudo labeling, because if it's not accurate, then obviously that's going to harm performance. That the generated and real distributions are close, or that adversarial attacks are unlikely. So random samples are not frequently misclassified by the pseudo labeling classifier if under the adversarial attacks. And that generated samples should cover the manifold of real images, so that there's a non-zero chance of sampling a real image. And yeah, so then we explored this with varying generative models. So on the bottom we have VDVAE, BigGAN, StyleGAN, and DDPM. And what we can see is that for all models, we're able to improve over not using any synthetic data, but that with the DDPM, we're able to improve the most and by a significant margin. And what's also interesting is that even with using just synthetic data, we're doing better than using real data. So when we look at the results, we see that we do better than the previous state of the arts on CIFAR 10 under L infinity, under L2 in terms of robust accuracy, CIFAR 100, SPHN, Tiny ImageNet, and even ImageNet. And then we're doing better on both the clean and the robust, which is challenging, as we discussed before, that there's maybe to some extent an implicit trade-off between the two. So now let's move on to what do we do if we don't have that kind of very nice LP norm perturbation definition that we can use to construct our loss function to optimize over. And that's because the LP norm is obviously not descriptive of real world perturbations or real world domain shifts. So for example, we can have quite simple ones like rotation translation, we can have differing lighting conditions and differing skin conditions. So here we're showing like how this can happen for a classification task. So we have a model that says it's 99% confident that this person's not smiling. We add some semantic perturbation, which is like a change in brightness. And now the model is very confident that the person is smiling. And so this was work that was done by Sven and others on using disentangled representations to improve robustness in the wild via adversarial mixing. And here the idea is to go beyond LP norm bounded perturbations by providing a formulation to describe arbitrary variations. And they focused on using StyleGAN for their test case. And what they demonstrated is that they can create models that are robust to perturbations beyond LP norm, particularly in visible image variations. So they use disentangled representations, and then what they found is that using these disentangled representations, you can just fall back to using the original usual toolkits, so like adversarial training or verification that operate on LP norm. And then they demonstrate that using such a method, you can get results that are less biased with respect to the perturbation of interest. And the motivation for this work comes from the fact that it is known that a lot of classification models are not fair when you look at gender or when you look at skin tone, and in particular when you look at the product of those two properties. So if you look at darker male, darker female, lighter male, lighter female, you can see that there are very large gaps when you look at the, say, darker female class. And so this is potentially a way to mitigate some of these kinds of failures. So if we look at the adversarial risk that we had before, originally we had the delta over set S, which was over the LP normal. And now we're going to have this optimization over T, where T is a set of input transformations that do not alter the input label. And to define the set of input transformations, we're going to assume that we have access to a perfect generator. This is going to be StyleGAN. So we have some generator that has a latent space, and then from that latent space decodes to your input space, so the images. And then we can decompose that latent space into a set of latents that are important for the classification task and those that are irrelevant. And then the idea is that we have our image, which is a function of those two parts of the latent, and we have a probability, and therefore the probability of the label given the image can be decomposed and is actually just a function of the important latents and not the irrelevant latents. And then what we do is we construct our test set, and what we can do is we can again have this kind of perturbation set. But now the perturbation set, as opposed to being within the LP normal, is around this irrelevant latent. So we can perturb that irrelevant latent, and the classification should not change. So if we had that, so we had the adversarial risk that we had before, and now we modify it to be just with this new set T. So this is going to be admix, which is the new adversarial risk that we're going to be using. So in order to implement adversarial mixing using StyleGAN, NVIDIA's, they use NVIDIA StyleGAN, which creates highly realistic faces. And it also has this nice property where you can get a disentangled representation that allows control over coarser and finer details. Because it has this nice property of style mixing, where certain parts of the latents are going to be about the semantics, and other parts of the latents are about the style properties of the image. So for example, here, this the different rows are where you have fixed the like semantic or the content parts of the latent, and then the columns are where you have fixed the style. So you can see that it's always like a woman, she's in the same pose, she has the same expression, but that the style, like the color of the hair, the background, etc., is changing as you change the style parameter. And yeah, there's been later work that has built on this and demonstrated other ways that you can actually operationalize this idea. So how we, or how they went about doing this is that you first generate some random latents. You then mix with latents of the clean image, which you can just do offline. You synthesize a new image, and then you classify it. And then what you want to do is you want to find your random latent that's going to lead to a misclassification. And then you just have your standard adversarial loss over that. And if you run this on Celeb A, then so Celeb A is like a non-synthetic data set, which StyleGAN can generate high quality images of. Then we find that adversarial mixing outperforms the baselines. So you have your nominal setup, which has accuracy across the different attributes. And then with adversarial mixing, you can actually improve over that baseline and the other baselines in order to achieve the highest performance. So it shows that actually being able to use this method to make our models robust to a given specification, where the specification is that the classification should be robust to the style latent, actually gives us a model that is more robust and performs better than just with nominal training. So now I'm going to move on to some newer work that we have just kind of put up on arXiv. And here, what we want to do is to be able to go beyond anchored failures and visual explanations. So we have, we had some like LP norm perturbation, where we had the panda with some epsilon, and then we that changes the prediction to a gibbon. We had some semantic perturbation where we are not smiling, and then some semantic perturbation, which then gets changed to smiling. And what we can think about this is we can think about these images to the left as being anchor images, and these perturbations as almost like being explanations that we want to be robust to. And this kind of idea, or this approach of trying to, make sure that our models are robust and be able to find failures of these models, is quite a common thread in the vision literature. So if we first think about how are we actually going to verify that our vision model is robust, we have different ways that we can go about doing this. So here, we had this clear specification, which came from the LP norm ball, or came from the kind of style content separation in the latents that could give us some like semantic perturbation. But if we don't have that, then it becomes harder to think about how are we actually going to verify that our models are robust. And so one way that we can do this is to try to collect real data. So Hendricks et al. Have been really good about doing this. So they have these interesting data sets such as ImageNet A and ImageNet O, which are natural adversarial examples, and they evaluate how model performance degrades when inputs have limited spurious cues. They also have collected 4 real-world data sets to understand how models behave under distribution shift. But that's quite challenging because you have to go out and collect these data sets, and it's very limited what you can collect in order to investigate whether a model is robust to that. So then other people have tried to create synthetic data sets to explore specific problems or properties of their model. So for example, Hendricks introduced ImageNet C to explore whether models were robust to a synthetic set of common corruptions. We also had Garros, who looked at whether models were robust to texture shape cues, or whether they, the models have a propensity to overemphasize texture cues. And then there were others that investigated whether models are biased towards background cues by compositing foreground objects with various background images, and found that yes, the models were taking advantage of background cues. And then for the automated tools, it's what we all know, adversarial examples. And this isn't just in images. You also have language-based templates, which can be used to generate test cases for specific failures. And then there was the works that we just discussed, the one on using StyleGAN to go beyond these hard-coded rules of LP norm robustness. But they're very difficult to automate because you need the generative model itself to be kind of disentangled, and it also limits what you're able to explore. So we had this work on discovering bugs in vision models using off-the-shelf image generation and captioning. And here the idea was, how can we go beyond this? So, as we were saying, it's hard to evaluate models on how they will perform in various scenarios because we don't have many options. For example, label data is scarce. And, if we wanted to create another label data set like Hendricks et al. Did for ImageNet A, then we'd have to scrape the web for more images, rate the images, and that's quite expensive and can't be done on a massive scale. We also could create synthetic data sets, but then, as we discussed, that requires some human creativity to come up with the kinds of cues we want to explore. So do we want to explore texture versus shape, or background as a potential spurious correlation the model is using? And then we also have the automated tools of, say, LP norm robustness, but these are very narrow in a way. While they are very clear and precise. They're not open-ended to various more general spurious correlations. And so in this work, we describe a methodology for discovering failures in image classifiers automatically by using off-the-shelf large-scale models. So our approach doesn't rely on collecting new data sets or manually crafting heuristics. And we have a nice property that the failures are human interpretable. And we do this by clustering and captioning inputs on which the classifiers fail. And then what we can do, which is quite interesting, is we can modify those captions and use that to produce alternative hypotheses of why the failures occur. So we can do some analysis to figure out what the real cause of the failure is. And finally, we demonstrate scalability of the approach by generating adversarial datasets, similar to ImageNet-A. But unlike those ImageNet-A, our new generated dataset is more similar to the original training distribution of ImageNet and can generalize to multiple classifier architectures. So as a preview, here are some examples of failures. So you can see that the upside down mushroom kind of looks like a candle, and the robin on the branch looks a little like a lizard with the red neck. So here we describe the setup in brief. So we assume we have a classifier that takes images as inputs and maps them to a set of labels. We also have some true distribution over images conditioned on a label. And we also have some distribution of images conditioned on a label and a caption. And the aim is to find a caption such that the failure rate when generating images of a specific label is much less than when generating images given the label and the caption. So the idea is that the caption is describing something that leads to, that is a spurious correlation, and so the model starts failing a lot more than it would originally. But of course, we don't have access to this true distribution, and instead we have access to p hat, which is like a text image and image to text generative models, which are approximating these true underlying distributions. And so how this works in more detail is that we have 4 steps. In the first step, we generate images from the baseline prompt. So we construct the prompt given the label, so like a realistic photograph of a fly insect. And then we measure the failure rate by just, say, generating, say, 1,000 images or more, and then looking at the number of times that the classifier misclassifies that image. So then once we've done that step, then we have a bunch of images that were misclassified. And now what we do is we cluster these images using image similarity in some feature space. And then we get a cluster, and then we caption the cluster. So here we find this cluster of images, and we caption it a realistic photograph of a fly insect. It is on a yellow flower, the background is green. And then what we do is that we generate more images according to these captions. So we take that caption from the cluster, we generate a bunch more images, and then again, we classify and measure the failure rate. So here, what you can see is that the failure rate has gone up. And if we were to look at a target failure rate, so for example, B here, as opposed to just how often is it misclassified for fly, we can see that that specific target rate has also gone up. But now, okay, so we have some new failure rate given this modified prompt or this new prompt, and then we can compare the failure rate to the original failure rate, and we see that now we have a lot more. So this implies that there's some spurious correlation that the model is using within this cluster, and that's leading it to these misclassifications. But then an interesting thing we can do is that we can query this caption, and we can refine it by, say, removing subclauses or removing adjectives to try to find the minimal description of this caption that leads to the same failure rate. So for example, here we take a realistic photograph of a fly. It is on a yellow flower, the background is green. And then we can modify the caption to get a realistic photograph of a fly. It is on a flower. And this simplified caption has the same failure rate as the original caption. So this implies that the cause is that the flies are on a flower, and this is leading to these misclassifications. So to investigate if this method works, we used these two examples. So we picked two random classes, fly and crayfish, and two target classes, bee and chain link fence. So just going back here, so in this example, we're going to be looking at the failure rate for a specific target class and comparing those failure rates. So here, like how often is fly misclassified as bee, and how often is fly misclassified as bee when we change the caption. You could also look at it on just misclassifications for the fly class, but here we'll be looking at it for a specific target class. So here we have, we run this pipeline initially. So we just use the base caption, a realistic photograph of fly or a realistic photograph of the crayfish. We get some kind of failure rate for each of the different top classes that the model is misclassifying images as. And you can see that bee is quite low down, and actually chain link fence doesn't even appear here. But when we find our new caption, according to the process that I just described, then suddenly failure rates jump. So here we have a realistic photograph of a fly, it is on a flower, and a realistic photograph of a crayfish, it is in a net. And the failure rate for fly to bee and crayfish to chain link fence has increased by 497x for the first and 3,000, or about 4,000x for the second. And if we look at the target misclassification, bee has suddenly gone to the top, and chain link fence has also gone to the top. So we can see that these are probably spurious correlations, which potentially make sense, as bees are often on flowers, and the net, visually looks a bit like a chain link fence. Another interesting thing that we can do is test out whether these failure cases arise under different generative models. So here we generated 30 images with DALL-E 2 and Stable Diffusion. And we generated them with the original prompt, so a realistic photograph of a fly. And then with the new prompt, it is on a flower. And then we look at the number that are correct, number incorrect, and the number target. And first we can see that when we add the it is on a flower, then the number that are misclassified for the target class, so for the bee in the fly case and the net in the, the chain link fence in the crayfish case, that increases in all cases. So for DALL-E 2, we go from 7 to 9 and from 5 to 4. We go from 0 to 9 for the base prompt, and then from 0 to 4 for the crayfish setting. And we can also look at Stable Diffusion, and we see the same thing. And we can also, this is maybe a side point, but we can also look at the other types of failure cases that arise. And we see, for example, that for it is in a net, we get spiderweb and strainer. And again, we can kind of intuitively understand that this is probably because of the visual characteristics of the image, that the model is focusing on the kind of the net, which looks a bit like a spiderweb or a strainer, and not on the crayfish. And finally, we can look at actual images. So we can use Google image search with the same captions, obtain, again, 30 images in each case, and again, see how do the failure rates change. And again, quite interestingly, is that we see that the number of failure rates for the target class goes up from 0 to 2 in the fly case, 0 to 4 in the crayfish case. So this implies that these failures that we're finding, they're really quite general over different generative models or even approaches to getting the images, and that they are probably a failure of the actual model and not just, and not just kind of a random thing that we find for that given generative model. Here we visualize more open-ended failures. So here the word in green is the correct class for the image, and the word in red is the incorrect class. So we find, for example, that the Jeep is misclassified as a snowplow, presumably because it's in the snow, and I believe that this is something else that has been found elsewhere in the literature. We also find, for example, that the jellyfish is misclassified as torch, and that's probably because of the color of the jellyfish. So you see that we can find quite a large number of these kinds of failures quite easily. Another interesting thing is that we can scale this approach to generate a large number of failure cases. And we do this by we take a model and then we find failure cases for that model. And here we looked at a data set that was created by fooling a ResNet 50 or a VIT. And then we looked at, do these failures transfer to other models? And we find they do. So for example, for the ResNet, the failure cases transfers 78% of the time to another ResNet. And the VIT transfers about 77% of the time to another VIT. But we can also think about transferring to other models, larger, harder models. So here we looked at different VITs, Inception, and ResNets. And we also explored models that were pre-trained on ImageNet 21K. And what we find is that the models that are better, so those that are pre-trained on larger data sets or larger, they are more robust against the generated data sets. So here we have 39%, 53%, 46%, but they're not universally robust. So we're still finding failures that transfer to these harder models. And finally, I'm going to discuss some of the limitations of this approach. So while we can find failures at scale, there's a number of limitations that we are hoping to overcome in the future. So the first is coverage. The generative model is unlikely to generate objects and animals in uncommon conditions. So for example, here we have a Persian cat in the snow. And if you give that caption to the generative model, it's able to generate it no problem. But actually discovering that failure case is very challenging for the model. Second issue we have is bias, where the generative model may overrepresent certain objects or conditions. For example, blue crayfish are really rare in the wild, but overrepresented by the generative model. And that's probably because people get really excited when they see a blue crayfish, take a photo, upload it, and as a result, we don't have an actual distribution that quite matches what happens in the real world. There's also captioning issues where it can be very difficult to describe precisely why a failure arises. So here the crayfish is confused for a net, but how to explain the positioning of claws and the pose such that the generative model creates similar images is challenging. And then we also may have generation issues. So sometimes the generative model does not precisely follow the prompt. So here the salt shaker was in the prompt, but while there is salt in the image, there is no salt shaker. So we have shown two methods for improving robustness to specifications through standard adversarial training or a modification that works in the latent space of a generative model. We've also shown how to find failures according to more of like a natural language specification, which cannot be written down formally in the bugs and vision work. And in the last few minutes, we want to take a step back and think about what we need to build reliable, trustworthy AI. So if we think about the pipeline for creating and deploying an ML model, we need to first collect data for train and eval. We then need to train and fine tune our model. We need to calibrate it on some test set, then evaluate the model, make sure it is working as expected, and finally deploy it. And so if we want to make the system reliable and trustworthy, we need first correctness throughout. So we need to enforce correctness at each step to enable our models to be robust and unbiased. And this relates to the adversarial work, given a specification, how can we make sure to satisfy it? And the second, we need to be data and human driven. So humans can give specifications of what they want, but it's not necessarily clear how to relate or investigate if a model does not satisfy the specification. And this can be especially true if the data is imbalanced. And so, our evaluation data set may not fully cover the parts of the distribution we want to be robust in, and also the full distribution. And so here we demonstrated a method to automatically find failures of a model in an open-ended manner without requiring building a new data set. And finally, we need adaptability. So we need our models to be able to adapt to new specifications and requirements with minimal fine-tuning. And we haven't discussed a method here, but we think it is an important component of a reliable and trustworthy system, that it can adapt quickly given new information or after a failure is spotted. And to some extent, we can think of adversarial training as doing this, but how can we do that for the less formal specifications that are in the kind of bugs and vision work is less clear. So I think that is it. Thank you for listening, and I hope it made sense. I had to take over from Sven very last minute, so again, I hope that part of the talk made sense, and if you have any questions, then please let us know.
Thank you, Olivia, for taking over. But I'm now seated and I can actually answer as well questions if there are any related to the first two parts. So.
Hello, hi. Am I audible?
Hi.
Hi, I'm Gargi. Thanks for the really nice talk. I'm a master's student at UIUC, and I work in both areas of robustness with Professor Bowley. So I have a query on the third approach which you presented for failure discovery. So you're doing an ablation on the generated prompts to identify the possible spurious correlation, I assume?
Yes. So do you mean this part?
Yes, the previous slides where you show the methodology. I assume you're relying on the caption to identify, to do an ablation on the caption keywords and identify the underlying possible spurious correlations?
Yeah, kind of. So the idea is that we take the two captions that we find. So we say we have the original caption, which is just like a realistic photograph of a fly. And then we have the modified caption, which is a realistic photograph of a fly. It is on a flower. And then we compare the failure rates for those two captions here. And then the idea is that if the failure rate for a specific class or overall goes up significantly, then that is probably a spurious correlation causing failures in the model. Does that make sense?
Okay, got it. And I don't understand how you scale this up, because I assume the captions still have some requirement of background knowledge on what to change.
So there's kind of 2 points to that. So first, the captions don't actually. So in this setting, we actually just start with this original prompt and then generate loads of images according to that prompt, find failures that arise just from there. Mm-hmm. And then we caption those to find clusters, and then we use that to find failure cases. So that aspect doesn't require any additional information. However, so we use that in order to generate these, and we have quite a lot more in the paper. For the part where we're talking about the data set generated from the ResNet and the VIT, I kind of glossed over the details of precisely how we did that. And here it is a bit like, so it's not that we can't do the previous thing, it's just that it would take forever in this current setup, or it would take a very long time. So to speed things up, we use instead a set of prompts that we think will cause failures. And we get those prompts by captioning images in ImageNet A. That gives us an initial set of prompts. And then we use those here to generate the failure cases. But one of the things that we would want to explore is like how to speed up finding failures. So we didn't need necessarily that step. But yeah, that's good.
Right. Okay. Yeah, that makes sense. And I assume that all of these failure cases are still at the distributional level. So we're not talking about adversarial examples at this point for this part of the talk.
Not precisely, in that, like, yes, here we're motivated by the more semantic, but we do find that there are some that are probably more adversarial in nature. So an interesting thing that we didn't do yet is to kind of classify the different failures that arise and what type of failure that they are. Because we do find that there are some that seem to be more adversarial in nature.
I
But
see. So
that is in this data set, whereas in the clustering case, you wouldn't get that because you would need to cluster the images in order to caption the failure case.
I see. Yeah. So when I meant adversarial, I meant imperceptible changes in the images, which would not be captured by the captioning method.
Yeah, you're right. So that is not what we're focusing on here.
Right, right. Okay. And my last question is that why do you say bias is bad? Because if my model is seeing more of the minority groups, my model will be invariant, hopefully invariant to the spurious correlation. So why do you say bias is bad, or why is seeing more of minority groups bad in this case?
I'm not sure. That's not quite, I think, what we mean by bias. So maybe there was some confusion there. I think what we mean by bias is that the model wouldn't have seen enough of the minority group. So it might be relying on features that only exist for, say, the larger group. And so as a result, doesn't generalize to the minority group.
So you mentioned that some generative models create more of blue crayfish, but in reality, they don't exist.
I see.
So yeah.
Yeah. So I suppose in that specific, if you're looking at it from that specific perspective, it's not such an issue. In that, like, if this is a minority group that you want to be more robust to, and this is finding that failure, then that's great. That's kind of what we want.
Exactly.
But
yeah.
it could be different. So it could be that the bias is the other way around, where you get none of the minority group, and then you're not able to find that class. So maybe that example doesn't make you think of the right thing, but the general problem is, a problem.
I see. So basically having some subpopulation severely underrepresented in whatever manner. Okay.
Yeah.
Okay. Thank you.
No worries. Are there any other questions?
A follow-up question to that, Olivia, is this more of like a so like you and Sven's take on the way you executed this idea, and like more precisely is, if I got it correctly, the model here is not guided. Was like, if assuming that that statement is correct, was it a deliberate choice to keep the misclassified examples on manifold, since the misclassification can be an objective, and so like a guidance signal can be incorporated so that the network, so that the diffusion model or generative model generates the mazes that are more likely to be misclassified. But then again, those can be easily out of distribution. So it's like, was it a deliberate choice? And if yes, what made you sort of like do it this way, since there were many other ways to execute it?
I think Sven has thought quite a bit about this, so maybe.
Yeah, so it's definitely a thought we had, like, why don't we guide, the diffusion process to generate failures? But what we really wanted to showcase as an initial prototype is really that you can apply this to any black box classifier and kind of any generative model that is good enough, obviously. And so we wanted to abstract away the fact that, one, it was a diffusion model, and two, that you had white box access to the classifier. So maybe that answers your question. But yeah, definitely being able to leverage the fact that you know more about the classifier and you know more about the generative model could make the search for failures much more efficient.
I see. Yeah, I guess in hindsight, it keeps the approach very clean, and if you do get a lot of misclassified examples. I guess guidance is a Pandora box. Like you never know. Like it might generate out of distribution samples, and there's no way of figuring it out in an automated manner.
In fact, we could use your work on this.
Thank you. Say not to hold the mic here, but if somebody else doesn't have a question, I have another follow. Okay, in that case, again, this is regarding the first work that Olivia you presented, and it's again more on the asking, like sort of like what's your opinion per se, and that would be regarding synthetic data. It's been quite a while since you guys did this work, and what has been your sort of take on synthetic data? And let me make it very, very objective. So synthetic data is great. This plot speaks to it. But there is a diminishing return. I think Sven, you quoted, if I remember correctly, at some point in our conversations too. For example, it can boost robustness by 7%. It can boost accuracy of a ResNet from 93 to 96. But it cannot change the CFAR10 state of the art from 99.6 to 99.7. Like it doesn't add the value where it matters the most. It's more like relates to your third point, is the gap between real and synthetic data. Like their distributions are close, but still, like maybe near the tail, the generative models aren't good enough. So given how much the community has improved, what has been your team's experience or your thoughts on it in the last 2 years? And where do you see, like in the next 5-10 years, it being like, would it change a lot? Or would this sort of like, the fake will never be as good as the real thing?
I mean, I'm happy to take like the initial answer, and then Olivia can add on to that if she wants. We've definitely seen that, you know, generative models are becoming better in two ways. One is that they have higher quality of images, and two, they also have very large diversity of the images that they can produce. So they can basically, you know, from a given training data set, they can try and compose images in a way that a classifier doesn't. So in some sense, because you force the classifier to respond to a specific objective, it can ignore or, you know, enhance spurious correlation in some ways, like ignore important aspects of the image, or you know, overemphasize some others, which like the generative model, which has to generate the full image, kind of doesn't. And so that's definitely one thing where I see like the loss that generative model use is kind of quite different from the loss that classifiers use, and then that's why we can sometimes leverage generated data to our advantage. That being said, it's kind of a double-edged sword in the sense that it can also backfire, where like you can't invent new information in some ways, right? You've seen your 50,000 images from CFAR10. The fact that you generate 1 million now technically shouldn't give you more, like you shouldn't have more information from the synthetic data than you had originally in the training data set, which means maybe the answer is not really synthetic data, but the answer is just to improve, you know, losses or like self-supervised losses. Yeah, anyways, that's my early take. I don't know if Olivia has more to add.
No, I think that's yeah, that's like, I think I agree with that take. I think for me, synthetic data has two possibilities. So the one is, yeah, the kind of like the ability to compose features, and there's also another benefit that's maybe like not as obvious when we think about ML systems, but that when we create synthetic data, we can reuse that synthetic data for any downstream model that we train. So we don't need to like come up with a new loss or a new weight decay hyperparameter, et cetera, for each new model that we try to deploy or that we try to develop. And I think that's like quite a practical benefit. And then I also think that this synthetic data is quite an interesting, I think it has a lot of potential that we haven't like quite explored yet. So we're starting to explore that in the bugs and vision work. And I wonder if there are other ways that they can be used to improve robustness of models that's not kind of necessarily even just the data augmentation, but is like other use cases. So maybe that kind of doesn't more around your question than answering it, but those are some of my thoughts in addition to what Sven said.
Yeah, thanks a lot. I understand it was a very open-ended question, but yeah, thanks a lot for taking time. There's one in the chat actually.
Yeah, so they're basically the person is basically asking about how, like, if we trust that large text to image generative models generate the correct caption, and does that mean they're just better, and can we use them as classifiers? Or do you think they have a different failure mode to a discriminative model? I think my thoughts around that are, first, that is an assumption we make, and it's not always true, as we showed, or as we didn't necessarily show in the failures, but that's not necessarily true. But the other issue is that, yeah, I do think that they have their own failure modes. So I think that in general, they'll be more accurate, but then they are both going to be used in more open-ended ways in terms of being used potentially more like VQA style setups or just on more generic data as opposed to ImageNet distribution, which then means that the area or the distribution of possible failure cases goes up quite a lot. And so even if they fail less in a specific one, if they're used in a lot more cases, then they will have many failure modes. But yeah, they're probably fewer failure modes than what we get with the classifier. We did some very cursory experiments looking at transferring some of the failures we found, and some of them do transfer at a much lower rate, but there is some transfer as well. So yeah.
Thank you.
In fact, it's probably the holy grail, like the model that can self-debug itself. But, yeah.
Do we have any other questions for the speakers? All right then. In that case, I think we are finishing right on time. And let's thank our speakers for the amazing talk and the very engaging discussion at the end. Yeah, thanks a lot, both Sven and Olivia. Sorry, there's a question.
No, I was just saying thanks for organizing.
Yes, certainly. By default, the recording was on. I didn't ask it earlier. If you don't mind, we will upload it on the channel. And yeah, we'll do that by tomorrow something. And yeah, let's see you everyone next week then. Next week is the break. Yeah, thanks a lot again. Bye bye.